Yo, what's up guys? Welcome back to day 17. Changed the title this time. Now it's just called IntelligenceMaxxing. Because I'm not look maxing, but IntelligenceMaxxing. And what I'm going to do today is probably do some work on my deep learning homework. So I have this homework assignment due in 3 days. And I'm like maybe a quarter, not even a quarter way through. So gotta start doing it. And I think what I'm gonna do here, alright, so this is one of the questions I have. Compute the derivative of a loss function, j of w with respect to w, where j of w is equal to 1/2 sum of w transpose x minus y. Okay, so I think this is going to be equal, so yi plus two plus yi plus, so the max one is m. Right, so if we expand this summation out, what we're doing is we're just adding up a bunch of these so w transpose x1 minus y. So this is our prediction plus the second prediction plus the third prediction, and we just take the absolute value of that. Okay. So this function is just adding up all of the error from each prediction, taking the absolute value, then dividing by 1/2. Okay, I wonder if there's a special rule when taking the derivative of a function with an absolute value. Okay, so what I think it's, there's one thing. And, okay. There's also a so 1/2 term to multiply to the summation. So there's something, this is where we do slash big slash big. Oh, no, we don't want the sum actually. Every term. Alright, because then this will be 1/2 times W transpose x1 minus y So I think the derivative is just going to be 1/2 x, 1/2 times sum of absolute value of x. This is taking derivative of absolute. This is where I'm going to ask ChatGPT, what is the derivative of an absolute value? The derivative of an absolute value function, therefore, depends on whether x is positive or negative. Okay. So if this is negative, then it just takes the absolute value of that. If it's positive, then it doesn't. So it seems like people online are saying that there might be a piecewise function here. So I'm just gonna skip that for now. Just because that might get a little complicated, so I'll just go with part 4 for now. So I still haven't finished yet. Okay. JFW 0.1/2 M this is similar to the previous loss function, but of taking the absolute value, we our term is being squared, and there also is a squared regular term. Regularize regularizer term at the end. I'm not too sure. Okay. The L2 norm. Oh, I think it might be /L. Okay, so maybe again we can think about again squared maybe. And then we want to square it. So squared okay, so we're squaring all the terms, and then once we square all the terms, then what's gonna happen is oh, the 1/2 should cancel out actually. That's probably oh, okay. That's probably why. Okay, so then yeah, we're gonna eventually have to distribute this term to every single one. To approach taking the derivative of JW, I splits the summation and regularizer to two terms and differentiates both. Two separate terms and then different. Let's start with the summation first. From the expansion of chain rule is helpful for differentiating each term. So I think frac, so if you do dw of slash left slash right of w transpose x I just take this actually. Is equal to, and then we have 2, so that's the chain rule, times 2 times W transpose Xi minus Y I, okay, and then we multiply by X, and multiply by Xi. So 2x, okay, why did they do this? For differentiating each term, okay. So we have this, so this is the derivative of kind of this square deviation. Alright. And then so this term is repeated for all xi's, and yeah, okay, I guess we could do this for all xi's, right? We can treat each term separately, so the 2 and 1/2 conveniently cancels out. So the chain rule becomes that's we apply this same process to each term, so that eventually so it seems like the sum DDWs So that's eventually. Wait. Yeah, I think this is what we have. Oh man, this looks really hard. Oh. But this is the sigmoid function, okay. Is equal to sum of, okay. We have to multiply this. Okay, yeah, so we have the sum of all of these added up, and then finally the L2 norm is defined. Square roots of W1 plus W2 plus W. So it seems like it's just lambda. To each. This is tough. Okay. This makes. Alright, so that's the L2 norm, and then we square it, so we multiply lambda by every single individual w. Then our derivative is just lambda. Calculation. It's easier, so I think what we could do is then we could say that's dw of lambda times w equal to lambda just equal lambda. Okay. Combining two terms. So dw of jw is equal to sum of, right, plus lambda. Oh, dw. Shoot. Okay, so there's this one, the loss function. I think this is the sigmoid, so it's log of sigmoid. Okay, right. I'm gonna skip this for now, just because it looks a bit harder, but I think eventually I'll be able to do it. Tan h, I forgot how to take derivatives of these sine functions or trigonomic functions, except for sine and cosine. I think that's a bit easier. But yeah, skip that for now. Let's find the solution for the system of linear equations given by ax is equal to b. Okay, so I think what I could do here then is find the solution to the system of linear equations given by x. I can use those linear, what do you call it, operations. So I can multiply, divide. Easiest way for me to solve this is by setting up a matrix. Solve for x. So let's do this. Let's add this. -1. slash just do anything. Don't think so. Okay, I'm not too sure exactly. I can add that bar in the middle. Wait. How to create matrix. Array. I see, okay. Yeah, maybe this is a bit better. Okay. We have and eight. And -11 and -3. Do anything? No. Okay, that's interesting. B matrix, bar matrix. Okay, so I think if we, let's see what we can do here. We can try to cancel out terms to get 0. Then try to create a so then let's perform some operations. I guess some linear operations to make the the left side of the matrix the identity matrix. I think that's our goal. So we want this, for example, 1 1 0 1 0 0 0 0. So I think what we could do here is then we just add row 1, row 2, or row 1, 3. So, okay. Starting with adding row 1 to row 3. Okay. So I think this then becomes becomes 0, this becomes 2, this becomes 1, and then this becomes row 8 negative 3, this becomes 5. Text BF, so that's text BF. Okay, so that's good, and then we could also what else could we do? We could if I add one. Okay, right, so it's 2, here's 1, right, negative 1, 2, 2, and then I can add negative 3. If I add this to, so this will be 1, this will be 3. Or if I add this, then this becomes 0, this becomes 2, this becomes 3. It's just scaled by, okay. Yeah, or I could have just added this. Yeah, so this just, if you add this to that, it's okay, what if I added row 3 to row 2? So this just becomes negative 5, 0, 4, negative 5, 0, 4. All right, then I add this here. This becomes 0, 2, 1, 0, 2, 1. if I add this here, this becomes 0, -1, 0, 1, -1. Let's try that. Text bf row 2 plus 2 2 plus 3. Okay, so then this becomes 2 1 is equal to row. So this becomes -1, 0, 2, 1. Becomes -3. Right, okay. Right, and then we have, okay. So -3. Okay, maybe this could work. So we have row 2 is equal to 3, -3 times row 1, row 2. Okay, so then this becomes 0, 0, so this is still -1. -3 times 1 is -3 plus 2 is just still -3. So that's, oh, plus 2 is -1. And then -3 is 9. 9 plus -3 times -3 is 9. 9 plus -11 is 2. -2. Okay. So this is getting somewhere, it seems like. Okay, and then EF, so it'll be row 3 is equal to row 2 plus row 3, right? Okay, so we have row 2 plus row 3, and then we have something that looks like, after this I might have to go use the bathroom. Alright, so row 2 plus row 3 then becomes 1, 0, negative 3 plus 5 is 3. Alright, so we have that. Okay, yeah, I'm gonna use the bathroom now. back from bathroom. It seems like I'm running out of space here, so I might just have to shoot for the moon. Shoot for the moon here. So if I add this here, this becomes 1. Running out of space, so I'll just list a bunch of the operations and the final matrix. So we're gonna have BF is equal to, so let's do row 2 is equal to text BF row 3 plus BF row 2. Alright, and then so we add that, becomes -1, and then we negative row 2. Alright, so then that gives us 1, and then okay, and then text BF row 1 is equal to text BF row 1 minus row 2. Alright, and then we have row 1 is equal to negative row 1. Okay. Alright, so then this looks something like 1 0 0, and this is what it looks like, right? And so this is what we need to figure out, and then shift everything. So row 2 is equal to row 3 plus row 1. Alright, so that's 1. And then -1. So I think this would be, so this is 3, and this is -1, I think. Right. And then we have row 1 is equal to -1 plus row 1 plus negative row 2, so it'll be -2, +2. So I think this is just +2 then. Swap row 1, row 3, so we get 3, -1. Swap row 2 and row 3. Okay, so if we swap row 2 and row 3, then we get something that looks like this. Alright, so this is work though. If we multiply maybe we could just use Python here. Import numpy as np. Existing Jupyter, Python environments, Anaconda. Oh, I don't need to save this. Alright, so np.array. Actually, let's do we have 3, 1, -1, -3, -1, 2. -2, 1, 2. So A is equal to np.array. Does A look like? Oh. 3, 1, -1. Alright. So B is equal to np.array. 8, -11, -3, and x is equal to np.array. So we have 2, 3, 1. Print B transpose. Okay, so how do we do a that's x 10, -11, 3. It's close, but not close enough. Alright, so we had 2 times 2 is 4 plus wait, 2 times 2 is 4, right? Plus 3 times 1 is 7 times 1. Oh, I think this might be the reason why. -3, 101. There we go, 8, -11, 3. Okay, yeah, I think this should be right then. Alright. Okay, eigenvalues. Oh man. KNH, sigmoid, leaky, Rayleigh, Elu, sync. Okay, so eigen, so reminder. quick reminder, eigenvalues and eigenvectors of a matrix have the following relationship. So if I remember this correctly, so the matrix vector product is equal to lambda times vector x. I guess lambda b, where lambda is equal to, oh wait, lambda x, actually, it's the same thing. Lambda is equal to eigenvalue and x is equal to eigenvector. So I think this is the relationship. All right. And then if I remember correctly, we might have to subtract something on one side. So we have ax to find the eigenvalues and eigenvectors of a matrix. We can do it'll maybe, I think it's called spectral theorem. Not too sure if that's the right word for it. But I think it'll be helpful to find the eigenvalues and eigenvectors of a matrix. It'll be helpful if to move all terms to one side. So let's see. So it'll be ax is equal to minus lambda do some algebra to make this equation a bit easier to work with. Right, so I think the way we could do that is, so we subtract this, and this is equal to 0. And then we could say that, alright, so if we subtract and they equal to 0, so that means we could take out the x probably, and now we have something that resembles a minus lambda times I times x is equal to 0. Right, this is our identity matrix. So this is pretty much saying that a minus our identity. So a minus lambda times x is equal to 0. So I think that means within this matrix itself, we have a, so we're going to have to subtract lambda from the diagonal. And we have to solve for 0. This part is where I'm a bit iffy. How do we find eigenvalues? Why do we need to find the determinant? Okay, never mind. So note that once we get to this step, could be the case that does a determinant equal 0? Significance of a 0 determinant if it does not have an inverse. Coder. Okay. So, determinant of a minus I, could that just be equal to 0? Right. not have numbers. Identity matrix. Y is a lamb slash. So this is the characteristic polynomial. It's in that's some coffee. I'm gonna text someone real quick. So. Okay, let's see. So the characteristic polynomial. Excuse me. Invertible matrix. Zero is not an eigenvalue, okay? So why can't... So if the determinant of a matrix is 0, why can't an eigenvalue be 0? There is no solution. So why can't the eigenvalue be 0 for a non-invertible? Okay. Like half their pepperoni onions. Wow, Chris. Okay, let's go. It's actually not accurate. So why can't the eigenvalue? Collapse. No, non-invertible matrix class lower dimension. Okay. Then it is not invertible. So what is the significance of A0I? Okay, so Y is oh. Okay. I'm still kind of confused on why we take the determinants. non-zero vector v such that a non-zero vector v. Okay, so that is non-zero. That's important. Okay. Okay, so once I get to this step, it could be the case that x is equal to 0, but that contradicts the definition of an eigenvalue. So we need to be extra careful here. Okay, so I can see that if an eigenvector, so x could be 0, which is a non-zero vector, or which is a 0 vector, but from the definition of an eigenvector, it has to be a non-zero vector. And so I could see why, excuse me, a minus lambda I x is equal to 0. Okay. In order to ensure that there is a non-trivial solution, can be anything. The determinants of determinant can be useful here. Determinant of a matrix. So why is it an invertible matrix has no trivial solution? A is invertible, then for the equation x is equal to b, there is a unique solution for every b. X is equal. Gives the homogeneous equation for some b. Where there's the truth. So one eigenvalue equal to 0. Columns and rows are linearly independent. Okay. Nice, 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 nice. If A is not invertible, then for some b, equation ax is equal to b may have no solution. Okay, or for ax is equal to 0, it may have infinitely many solutions, or just the trivial solution, rather than just the trivial solution. Columns and rows are linearly independent. Okay. Determinant of a matrix could be useful here. Due to the solution x is equal to 0. That is a matrix whose determinants is 0 can have infinitely many solutions to the homogeneous system. Text BF AX is equal to 0. So I think this is the big thing here. AX is equal to 0. So then we can find the eigenvalue slash I vectors, can use the characteristic polynomial. So I believe this is the determinants of A minus lambda x times x lambda I x is equal to 0. This is called the characteristic polynomial. indicating that its columns or rows are linearly independent. All right. Okay, so actually, now that I have this, I mean, this is just the first step of understanding. So determine A minus lambda I. So I need to be extra careful. Okay, so for this we have a 3x3 matrix. The determinant of a 3x3 matrix is and this problem has a 3x3 matrix. To find the determinant of a 3x3 matrix, can expand the following. So determinants of A minus lambda I is equal to so we have, I believe we can choose the row column method. Right. So I look at this and I see that there's 2 zeros. Then what I can do is I can take this. So I take 0 times -9 times -8, 318. Zero. So I think 0 times the determinant of minus, wait, maybe plus, oh, -2 times determinants plus 0 times determinants. So I think we could do slash begin. Alright, so I think what I want to do here is probably creating a 2x2 matrix. Okay, so we have 1, 0, and then okay, so 7, I think it's -3. Oh, no, it's -9. 3, 18, -8. Alright, so we have that. So I think this should work for this one. Oh, shoot. Minus determinants of times I guess this could work. 0 times the determinant of this. Seven, -3, 18, -8. Okay, and then I think the last one is yeah, -9, 3. Oh wait, 7, -3, -9, 3. I think this is what. Oh, but we need, okay. Yeah, we need the diagonal. Give 8 minus lambda. So lambda. Okay. 8 minus lambda minus 2. Okay, so yeah, I think I forgot this here. Alright, and then also maybe this as well. Minus, oh shoot. No, this is not it. Minus lambda. And then last one is negative. Alright, 7 minus lambda. Okay, so then we have all the 0 terms cancel out. So this is zeros, this is 0. Determinant of this is just yeah.
Want to go to the gym?
Yeah.
15 minutes?
Sure, wait, can you help me? You wanna help me with some math stuff?
Yeah.
Alright, can you explain to me again why?
Oh my fucking god, dude.
This is a gift from Allison.
So, dude, she is giving you this is like really bad, right?
I asked her.
You asked her, can you give me this instead of a nice gift? Can you give me scratch offs?
Yeah.
She's enabling you.
Yeah. I was gonna ask you. So.
Did you win any of?
Yeah, I won $10 surprisingly.
On which one?
I like total combined.
Really? How do you know if you win?
I think it's just you're just matching it.
Hmm.
You have to match some of the winning numbers with.
Oh, these are the winning numbers.
Yeah.
So you got nothing here. And then also these 13 and 12 are some winning numbers as well, right?
No, they're not. They're.
So then what's the $100, $10?
Those are the numbers you have to match with the winning numbers, and then you get the prize whatever's underneath.
Hmm.
So let's say let's choose this.
On this one, did you win? No.
Yeah, I did. So
How?
I got 14. I matched with 14.
Oh, okay.
And so that.
So if you don't match, you don't have to check what was under it.
Yeah.
Okay, so you won $3 there. Here you won. Winning numbers 31, 33. You won $2. So $5, and then the exact same ones. You gotta get the game ones. Those ones are funnier. They're better. Okay, there you are. There's a game one. It's like Scrabble kind of, but with this to see it.
I'm streaming, by the way. If that's okay with you.
That's fun. You have any viewers?
Nah, 0 viewers.
Yeah. Okay.
Okay.
You're zero viewer Andy.
Yeah. I'm just look.
I farted.
It's okay.
Smell
it's
that?
called IntelligenceMaxxing Day 17.
Wow, you're intelligence maxing?
Yeah.
Wait, I don't see you on the thing. How late is your thing?
Oh, I think this is pretty late. Okay, just quick
Wait,
question.
check what it is live right now.
I don't. Okay.
That's a really bad. Oh, what's up?
Okay, quick question. So, can you explain to me why, if you take the determinant of a matrix and it equals 0,
Okay.
why that? Oh shit. Do you know why a determinant or a matrix that's invertible, if you have ax.
You want me to prove that to you?
0?
So you want me to prove why an invertible matrix has a determinant that's not 0?
No, why an invertible matrix has, if you multiply an invertible matrix with a vector x,
Mm-hmm.
and that's equal to 0.
Mm-hmm. If what's equal to 0?
If the vector x can't equal to 0.
What do you mean the vector x is equal to 0? They equal to the 0 vector?
Yeah, equal to the 0 vector.
So it's just 0, 0, 0?
Okay, wait, yeah. Let me.
If you multiply anything with like a 0 vector. So what do you want me to prove to you?
I think it's this code. Like, I'm trying to figure out how to calculate eigenvalues again.
Okay, so what do you want me to prove to you?
All right, yeah, let me write it down.
Okay, you got it.
So, ax is equal to 0. It says that like the determinant of a is equal to 0, then x does not equal to 0.
What do you mean? If the determinant, but a and x are separate. Oh, if ax is equal to 0, x can't be 0?
Yeah. Is that true? Is that possible?
I mean, I can think of a matrix with determinant 0 with a vector x.
Yeah.
It could be true. I mean, okay, so determinant A. Is A a 2 by 2 matrix?
It could be whatever matrix.
You can probably expand it. So let's say for a 2 by 2 matrix, you know what the determinant is. For a 2 by 2 matrix, it's AD minus BC, right?
Yeah.
So let's say for A, let's try and let's say 2 times 2 minus 4 times 1. This is not invertible. This has a determinant of 0, right? And you're saying no matter what vector I do, so in terms to multiply this by a vector, I have to do it 2, right? Because it has to be equal to this. So I need to multiply some x and some y where this equals 0, right?
Yeah.
Okay. So when you multiply this out, you're going to get, when you multiply a 2 by 2 with it needs to be, this is a 1 by 2, so it needs to be this, x, y, like that. So there's a 2 by 2 with a 2 by 1, so you're going to get a 2 by 1, right? Yeah, so you're going to get, I'm trying to think. Give me 1 second.
Do you just remember how to calculate eigenvalues and eigenvectors?
Not really. From linear, are you doing linear algebra?
This is for machine learning.
Really? Oh, wow. You're in machine learning again?
It's the next class, deep learning.
Oh, wow. Look at you.
Yeah, but I forgot this though.
Here, 2 by 2 times a 2 by 1 vector.
IntelligenceMaxxing.
You get a 2 by 1 matrix at the end. Wait, 2 by 2? 2 by 1 is, so it's above like that. A 2 by 1 matrix. 2 is the first number is the number of rows, right? And this is 1 row, so it is like this. So let's just redo it, right? So you have 2, 4, 1, 2. Then you have some random vector x, y, right? When you multiply this out, what do you get? You get you multiply the first row by that column. Then so it's going to be, I think, in the end, you just get, I Let me see. I mean, I can do what's it called?
Wait,
I think just to make sure that I'm right. I think what you get is
two
what
times
you get 2 times x and then 4 times
x. And
times
you
x.
add
So in the end you'll get like what? You'll just get 6x plus 3y equals 0, right? You'll just get that. I'm pretty sure. I mean, I can try and multiply this out.
I guess this. I mean,
Pretty
x
sure
and
here.
y can be 0.
Here.
So 2
Matrix
times.
multiplication
Oh, wait.
calculator.
How do you get this? It would be
Obviously,
2x
if
plus 4y, and then it'll be 1x plus 2y.
2 by 2, 2 by 2, 2 by 1, set matrices. Okay, so what did we say? 2, 4, 1, 2. Let's just put random value 5 and 8. If it calculates this, you get 42 and 21, and it was 5 and 8, so 42. So it's 42. That's not what I. 6 times 5 is definitely not 42. So I multiplied this wrong actually. Oh, you get. How do you get 2x plus 4y? Because you multiply the first. Oh, you multiply the first.
I think it's supposed to be a column vector.
Yeah, that is supposed to be column. So it's the first row times the first column, which is x, y. So you get, what is it? 2x plus 4y equals 0. X plus 2y equals 0. This is the same thing.
Yeah.
You divide everything here by 2, you just get x plus 2y equals 0. So, I mean, obviously x can be 0, right? I mean, think about it.
Yeah, x.
Think about it. Any matrice times the 0 vector should just give you 0. So if the determinant of A is 0, then of course x can still be 0.
Okay, then.
What were you trying to prove with it? Of course x can be 0.
Because they were saying something that looks like. Let me see this real quick. When you're trying to. Okay,
I'm taking this to all my classes next week. I hope you know that. Are
okay.
you?
The determinant of a matrix minus.
Oh, yeah, when you get the
equals
eigenvalue in
0.
there, then maybe. This is from linear algebra. What do you mean?
So
Determinant of A minus the
it's-
eigenvalues times the identity matrix.
Okay, it's just a determinant of A minus lambda I is equal to 0. And when you multiply. Sorry, let me.
So, okay, look. So basically, lambda is just an eigenvalue of A, right?
Yeah.
So,
And A minus lambda I x is equal to 0. Like for some reason, I guess by definition, an eigenvector, which is x, can't be. It's just a vector of zeros.
x is not an eigenvector. X is just something that's a solution, right?
Wait, so I thought an eigenvector is
Okay, wait.
a x plus lambda is equal to lambda x.
Hmm?
And so eigenvector is a vector that when you multiply a matrix by that vector, it just equals to.
It equals it. You said it's not equals.
No, sorry, that's
That's equals. Yeah.
I did plus. and
Okay,
that's
so
equals.
x is supposed to be an eigenvector here. So basically, I'm trying to think. So you're saying then if the determinant of A is 0, x can't be 0?
Oh no, okay. It can be 0.
That's what I'm saying. Like, of
But
course x could be 0.
I think what happens is there's more than one. X equals 0 isn't the only solution. I think that's.
Yeah, that's what it. There is
Yeah,
a non-zero. So I mean, think about it. Even for down here, there's a non-zero solution for x and y, right?
Yeah. It's
X
any
can be
any Y.
negative. No. If x plus 2y equals 0, you just have to set x equal to negative 2y, and then any solution of x equal to negative 2y,
Works.
you're there. Right? So
So X
usually.
can be anything then.
So if the determinant of x is, so it might be like if the determinant of x is 0, then there's, I forgot about this. If the determinant of A is 0, it could be a thing where there's infinite solutions, because there's infinite solutions. You can select infinite x and y where this holds. So let me give you one. Can I work on this or no?
Yeah,
On
go
this
for it.
end? Let me give you one that doesn't have, so 5, 1, 3, 7. This does not have determinant 0, right?
Yeah.
And it's like this, right? So then you get, and you want this to be equal 0, right? So then you have 5x plus y equals 0, and 3x plus 7y equals 0, right? So y is going to be equal to negative 5x. So then you replace y with negative 5, you get 3x plus 7 times negative 5x equals 0. in the end, you'll still just get x equals 0, I think, here, actually. But you'll only get one answer. You'll get x has to be 0. And, oh, but you'll get x has to be 0, y has to be 0. Okay, I think it's if this doesn't have determinant 0, then this has to be 0, the 0 vector. If this doesn't have determinant 0. Because look, no matter what now I have 3x minus 35x, you get negative 32x is equal to 0. So that means x has to be 0, which means y has to be 0. So I think if you have a with determinant non-zero, then for ax equals 0, you might need to just have x be equal to 0.
Yeah. Okay,
Here, let me see. So you can look real quick. And then are we going to the gym?
And then I'm gonna finish this problem and then we can get to the gym. What, can you click on it?
Here, yeah, see, look.
Yeah.
Prove that okay, so it's prove that ax equals 0 has okay, this is what you want to see, right? If determinant a is equal to 0. If it's equal to 0, then I think it has to be x is equal to 0. See, this guy says, assuming that the determinant of a is not equal, see, look, assuming the determinant of a is not equal to 0, the only solution to ax equals 0 is 0, right?
Yeah.
So.
Okay, makes sense now. Makes a little bit more sense now. Non-trivial solution.
Here, when does this have non-zero solutions? It should just be. What the fuck?
The rank of A.
Oh, it has.
Linear.
Yeah, it has stuff to do with the rank, and I completely. If I go through linear algebra again, it'll be, but like because linear algebra I did fine in that class. I did really well in that class, but I just forgot. I don't know how to calculate eigenvectors again, and what.
Yeah, it's okay. This is a good starting point. So thanks. I'll be done hopefully in like 10 minutes.
Okay.
Sir.
We're doing
Sir.
running after, but probably on the treadmill since we're there.
Oh, we can just run back.
But that's not enough.
Then we can run there and run back.
And then back.
Yeah.
That's too much then.
What?
Well, then that's too much.
Hey, get up. I thought you want to go, so let me finish this problem, man. Get up, get up. Damn, why is this heat so warm now? Yep. That is, can have, we'll have a non-trivial solution to. Okay, so once we're here, note that most of this evaluates 0, and just need to solve the middle term. So determinants is equal to, so the determinant of a 2x2 matrix, it's helpful to note that the determinant of a 2x2 matrix is A, so A, B, C, D is AD minus BC. Okay. Okay, this might be a little bit hard. -2. Yeah. Seven minus lambda plus 8. -8 minus lambda. Okay, so then this, yeah, this one's tough. Oh man. So this is equal to lambda squared. Okay, so we minus 7 times 8 is 56, right? Yeah, 56 -8 negative lambda. I think this is plus lambda minus 56, and then we plus, so 3 times 18 is 54. All right, 54. Two times, oh wait, I think this, yeah, okay, minus 2, lambda, oh wait, okay, and then we multiply lambda squared plus lambda minus 2. Alright. Alright, nice. Finding all the lambdas, finding all the roots gives us the lambdas. So this is equal to lambda is equal to -2, and then so it'll be -2. Just the lambdas. Okay, new page, maybe. Now, okay, now that's have the eigen values, can use them to find the eigenvectors. Alright, so I think with this then, we can plug them back into the equation. So we have, that might be something I might do later. Okay. Okay, yeah, I'm gonna go to the gym right now and then probably continue this. So I think there's activation functions. Okay, I could do those tonight or tomorrow. And then I think finding the derivatives. Yeah, that should be good. Okay, yeah, I also might I might finish this up later, but made some good progress. Alright, see you for now.